All right. Hello, everybody. How's it going? I like to take pictures of audiences, so do something fun. Come on, let's see ya. Let's go. All right. My name's Chad Lane. I'm a professor in the College of Education, and I'm here to introduce Neil Comins, who's our speaker tonight. I'm really excited that you all came and that we can do things like this. Neil is an astrophysicist and astronomer. He's an author of many books. If you've looked online at him, you'll find books, introductory astronomy books. Discovering the Universe is one of the top textbooks, but also popular books like Traveler's Guide to Space, which is out this year. Very interesting questions about how to get humans into space and onto other planets. And he's written two books called What If the Moon Didn't Exist and What If There Were Two Moons, which is going to be the source related to the talk we're going to hear tonight and get to enjoy. Neil's PhD is from the University College in Cardiff, Wales, and so he shares academic heritage with Gabrielle Allen, who's here, and you guys have the same advisor, Bernard Schutz. Bernard is his name? Okay, Bernard spoke here last year or 2 years ago. Last year. So very interesting connections at the University of Illinois. And the project Neil and I have together, we discovered all of these connections after the fact, after the proposal was funded. So it's been really nice. Neil has a fascinating career. He's been a competitive sailor, a paratrooper, a pilot, and of course astrophysicist and astronomer. The talk you're going to see is given over 25 times around the world. And in fact, it was such a success in Japan, they made a cartoon version of Neil that is part of an animated series that explores these questions. He's had over 150 radio and TV appearances. This fact blew my mind. Neil's first academic presentation ever was to Stephen Hawking's group. He was a graduate student. That was his first talk of his career. So everything after that's been a breeze, right? This is like all easy. You guys cannot stump Neil. I do want to tell you, Neil encourages audience participation. So if anyone has a question, I think we have microphones. We're recording this, so we'd like to get your questions on a microphone. But this includes attendees of all ages. So you really young guys in the back, yes, I expect questions from you. Any and all questions. Neil really does represent an amazing combination of creativity, of storytelling, of scientific knowledge, of education, really an inspiration to all of us in the field of doing work in education and science. So it's really my pleasure to welcome Neil Comins.
Thank you, Chad. That was wonderful.
Thank you.
Well, thank you for that very kind invitation. It's a pleasure to be here, and thank you all for coming. Since Chad mentioned Japan, let me just tell you one quick story before I get started. Back in 2005, I don't know if you've ever heard of the World's Fair or World Expo, they're now called. Well, they decided to have one, very good. They decided to have one in Nagoya, Japan. And Mitsubishi Corporation, which is actually 13 corporations, decided that what they would really like is to have the theme of their pavilion based on the moon, because the moon is socially, spiritually is very important in Japanese culture. And so they contacted me, and their pavilion at the World Expo ended up being What If the Moon Didn't Exist by Neil Comins. And so I went there and I helped them several times, to develop it. And it was just absolutely wonderful to interact with them and see what they could do with the concept based on the material I'll be talking about. And as Chad said, if you have any questions at any time, please don't hesitate to ask. I would be more than happy to explain anything. Okay. The talk, of course, is What If the Moon Didn't Exist? But to get there, I want to take us through what the moon has done for us. And then, by the time I'm done with that, I expect that you'll have most of the answers already for what if it didn't exist. So that's what we're going to do, is we're going to take a look at what the moon has done for us, and therefore how it would change if it went away. And to do that, I was actually asked by the Discovery Channel, the History Channel, yes, the History Channel, to do a television show on this for them. And I wrote the show and I sent it off, and we did shooting. I went up to the Bay of Fundy, which, as you may know, has incredible tides, tens of feet. I mean, just unbelievable. And we did a lot of fun things. 2 weeks, I'm not making this up, 2 weeks before the show was to be aired, excuse me, I got an email from this fellow who says, "Hello, my name is something, and I am the new director of your show, and I've rewritten it. Attached, please see my version of What If the Moon Didn't Exist, or the history of the moon and the Earth." And I went through it, and I found at least 15 incorrect concepts in science. And I'm going to show you one of them now. But the really neat thing is that after that show was aired with all the mistakes, I mean, I sent the email back listing the mistakes, explaining why they were wrong, and he wrote back and said, "Scientists can reasonably disagree on these matters." I'm not making this up. And so, it was aired, and the wonderful thing is that in my class, I teach about 200 students in introductory astronomy. Each semester, I offer them extra credit if, after I teach them the correct science, they come to an evening show of that show. And if they can find at least 5 incorrect elements of science, they get an extra 5 points on their final grade. And needless to say, the room is packed, and they all find them. It's wonderful. So it's wonderful. Oh, it's all relative, but anyways. So I'm going to start by showing you a clip from that show. And let me just say that the backstory of this clip is the tides. Okay? So, and if you have ever thought about what causes the tides, I invite you to think about that now, but I'm not going to ask you what you think is right, because I'm going to show you something, and it may not be what you think it is. All right? So let me show you, and I expect you'll find that this clip I'm about to show is fairly universal as to the explanation for tides, okay? And it's completely wrong, okay? So here we go.
What's called a tidal bulge on both sides of the planet.
The moon pulls on the Earth gravitationally, and when it does so, it also pulls on the oceans that are sort of stretched up a little bit toward it. It pulls preferentially on the front side of the Earth, pulls the ocean toward it, then pulls the Earth a little bit less, and then the back side, the ocean is not pulled quite as far toward the moon. So that's why there are 2 bulges, they're called tidal bulges, on the Earth.
Okay? Conceptually, what she said sounds perhaps like what you've seen before or heard. Okay? As I said, it's not so much correct. And this was from that show, by the way, where the guy, the director, got people to say things. So let me tell you what really does cause the tides, and we'll go from there. I mean, it is the core, the heart of the story. There's another common belief, a misconception, that the moon orbits the Earth. Okay? Not true. The moon does not orbit the Earth. So what is really happening, and now we get into real science here, what really happens is that the Earth and the moon are waltzing together around a common point called the center of mass of the 2 bodies. Okay? It's like 2 dancers waltzing on a dance floor. You know, as they waltz around, the lighter one will move more than the heavier one, but they'll both move around as they waltz down the dance floor. And conceptually, the Earth and the Moon are waltzing around this common point. Technically, it's called the Barycenter, orbiting around the Barycenter. And the Barycenter, as you'll see in a picture in a moment, is what makes a nice smooth orbit around the Sun. The Barycenter is located 1,064 miles under the center of the Earth, under the surface of the Earth, excuse me, here, okay, about 5,000 miles from the center of the Earth. So the two bodies are doing this, okay? Is that conceptually everyone with me on this? Excellent. And so the process of this motion creating the tides is where I'm going to go with this. So let me do that. All right. Our best current theory of the formation of the Moon was that there was an impact, as you can see on the left here, of an object that struck the Earth and splashed debris from the Earth off the Earth into space, into orbit around the Earth. So if this theory is correct, and it's the best we have right now, the Earth once had a ring. And it didn't have a moon yet, it had a ring. And at that time, the orbiting debris, the ring, okay, started clumping together. Sometimes bits and pieces of it hit each other and stuck. Sometimes they smashed into each other and formed dust particles and floated away. But eventually, one clump became dominant. And the gravitational attraction of that clump on all the other matter in the ring became the Moon. Okay? There are technical problems with that theory. The chemistry of the Moon and the chemistry of the Earth are virtually identical. And so how that impact could have splashed the debris mostly from the Earth rather than from the impacting body, which would have had a different chemistry than the Earth, is still a work in progress. So we're not quite there yet, but it's the best theory we have, and it's probably in one form or another correct. Okay, so we have a moon and an Earth, and as I've drawn on the picture, you can see that the rotation axis of the Earth, when the body hit it, was tilted over from the left to the right here. And we'll talk about that later, but it is highly relevant to the effects that the moon has had on the Earth, and therefore what happens if it goes away. Okay, so once we had the two bodies orbiting the Barycenter, all right, then things started to happen. So let's just take a look at that. As I said before,
how long did that take, that process?
About 100, 200 years. In other words, the ring was only here for hundreds of years. I'm sorry, did you want to?
Can you repeat the question?
Yeah.
How long did that process take?
It was very short. The numbers from simulations, and they vary, are just a few hundred years that the Earth had a ring system, which is short by cosmic times, but that's what the simulations, or at least the ones I've seen, have shown. Okay, so the Barycenter, the center of mass, in this drawing of these two, what these are two pucks on a air table connected with a rod. They're spun around and pushed. So the motion of that point in red, which is a fixed point on the rod, straight line. The 2 points orbiting around, the lighter one does more motion, the heavier one less, just like the Earth-Moon system. So this is an analogy. Yes, please.
Yeah, sorry. On the previous slide, just for clarification, what exactly was the ring?
That ring was debris. It was Earth, dust particles from Earth splashed into orbit by the power of the impact. literally think of throwing a rock in water. If you're throwing a rock in the water at an angle, you have water splash up. Conceptually, the same thing.
Okay.
Okay, so we have the smooth orbit and we have the waltz, and the waltz is the key, the waltzing bodies. So let me talk about, well, here's a picture just to take the stick drawing and making it more realistic. So this is what it looks like in the real world. And the question is, of course, so what? So here's the so what. If I have the Earth here, the moon here, and they're doing this, okay, just focus on the Earth if you would. The Earth is, every place on the Earth is now going around in circles due to the gravitational effect of the moon. And, well, if you've ever been on a merry-go-round, you can make this connection rapidly. If you're on a merry-go-round and it's spun around, then you are going to feel a force, and you're going to feel a force away from the center. You're with me on this. Now, I remember when I was a kid, I was like about 4 years old, and I was on one of these old steel merry-go-rounds, and I was on the end, and a bigger kid spun it so fast that I literally flew off, okay? So I can relate to this issue here. The fundamental difference between the merry-go-round effect and the motion, the force that every place on Earth feels by going around the Barycenter, every place on Earth going around the Barycenter feels a force like the merry-go-round, but for a merry-go-round, if you're at the center, you don't feel any force. The farther you get away from the center, the stronger the force outward as you're being spun around. On the Earth, every place on Earth is going around the same size circle. Therefore, every place on Earth is feeling a force due to this motion generated by the moon's orbit around it with the Barycenter, feels a force away from the moon. So here's the motion again. This is the almost quite merry-go-round force, the outward, I call it outward force, meaning away from the moon. And it's the same everywhere on Earth. That's the fundamental difference between this and merry-go-round. But conceptually, they're both, outward forces. All right? And so the tides are created by an interaction between this force and the force of gravity, as she said in the clip. So let me show you how that works. It's a bit technical, but not really, but it looks, I'll tell you what, I'm going to get my laser pointer. Drawing moon here, Earth here. Now, it is absolutely true that the force of gravity decreases the farther you get away from any object. Okay? So therefore, in this drawing here, the force of gravity from the moon on the Earth is strongest right there. It gets weaker and weaker, conceptually similar to what she said. Okay? But at the same time, there is the outward force, the force that's always away from the moon due to this motion around the Barycenter. And it's the same everywhere. And that's key to doing this. So what we physicist types do when you have two forces acting, one this way, one that way, is you create a diagram showing the arrows representing the forces, and the longer the arrow, the stronger the force. It's a tug of war, literally a tug of war. And so you have on the left side here, gravity, the force of gravity out to the left is stronger than the outward force to the right. And therefore, in this drawing on the left side here, you take the tug of war between these two, and the difference between them is the total force at that point. In this case, you can see, I put it in blue here, the force is towards the sun. It's lifting up Okay, it's being pulled towards the sun, excuse me, the moon in this case. It is being pulled towards the moon. And you might say, aha, therefore we have a high tide on that side. And if you calculate how high the high tide could be from the force of gravity of the moon lifting up the water, maximum tide you could possibly get is on the order of 6 inches. And we have higher tides than that. So something else is going on too, but we'll get to that in just a minute. Going farther away from the moon, at the very center of the Earth, the force of gravity towards the moon and the force away are exactly equal and opposite. They cancel out. And on the right-hand side, the force away from the moon, the outward force, if you will, is stronger than the force of gravity. And therefore, the difference between these two, the tug of war, the outward force wins, and there is a total force on the far side from the moon, away from the moon. So there's a force towards the moon on this side, there's a force away from the moon on this side. This force is created by the outward force, not by the difference in gravity. Is everyone okay with this? All right. Now, as I said a few moments ago, if you calculate how strong the force of gravity is to lift water, it can't possibly lift enough water to make the tides as we know them. Furthermore, you calculate the outward force, and the same thing applies. They're equal and opposite, by the way. The strength of the force, the tidal force towards the moon, and this on the left and away from the moon on the right, equal, but opposite. Okay, so the question then is, well, if the water can't be lifted up, what causes the tides? Any takers? What causes the high tides if you can't just lift the water up? Any idea?
The spin.
What about the spin? Well, hang on.
Just the spin of the Earth.
Just the spin of
That's
the
all
Earth. The spin of the Earth is absolutely crucial, but that's not it. But thank you. Don't go away. The spin is entirely relevant to this story of what if the moon didn't exist. Any other ideas about what? Yes, please. Well, hang on. He's going to bring a mic down for you.
Is it related to the Earth moving around the Barycenter?
That would be connect. Oh, I see what you're saying. No. But thank you. No, these are really good thoughts. Really good thoughts.
The sun.
No.
Earthquakes.
Earthquakes cause tsunamis, but they don't cause the tides. I'm sorry, he's going to bring the mic over.
Maybe the tilt of the axis of the Earth?
The tilt of the axis. Oh, that's very interesting. No? Sorry. Hang on, he's bring a mic over to.
So gravity towards the Earth has to pull back?
Say again.
Gravity towards the Earth has to pull back because the water is attracted towards the moon, and then...
The water is attracted to the moon.
Yeah, and then it can't go forever. It has to balance with the Earth gravity.
What he said, if I understood correctly, was that the Earth feels a force of gravity from the moon, and the balance between the force of gravity and the Earth pulling back create the tides. You're not wrong, but that's not quite it. That's very good. Very interesting.
Maybe
yes,
as we see there in shape 2, maybe the tides are created by the Earth kind of squeezing the waters and the remaining waters just going someplace else, causing the tides.
You are so close to being right.
Oh no.
You are so close to being right. The word squeezing is the only thing that's... Go ahead.
Sloshing. Just
sloshing, yeah, you're absolutely there. So let me take it from what they said and what he said to the explanation. The high tides are caused by not this water being lifted up, but by the water around the Earth near the poles, or almost perpendicular to the Earth-Moon line. This water up here all the way around being pulled by the gravity of the moon to fill this region here. So the water near the poles is being pulled away from the poles by the gravity of the moon. That's easy. That's not the 6-inch thing. The 6-inch thing is literally the water being lifted up here, okay? That's hard to do. Yeah, six inches. But over here, this water is being pulled in the direction that it would like to flow along the surface of the Earth by the gravity of the moon. And that water is then pulled to become a high tide. Does that work conceptually? Likewise, the water on this side is being around here, the polar ring, if you'd like, is being pushed away by the outward force, creating the high tide on the other side. And that is what causes the tides. Okay? But
at the end, it's the moon that's causing the tide.
The moon causes 2/3 of the tides. The sun does the same thing, causes 1/3 the tides. Do you want to? No, he wants to record it for you.
It's because common knowledge is that the moon causes the tide, and so you said in the beginning that this is wrong, but we are seeing that in the end it's the moon that is causing the tide. It's the gravitation of the moon that is acting in the pole and pulling out the waters and making this.
I don't believe I said the moon didn't cause the tides. I think I said that the explanation was wrong.
Okay. Thank you.
Was there another question here? Okay, so we have this water up here in the light blue pulled down by gravity from the moon, or flung away by the outward force over here to create the high tides. Therefore, 2 high tides everywhere on Earth all the time. Okay? Now, what I have not yet put in here is the spin of the Earth. The Earth is spinning once every 24 hours in round numbers. The moon is orbiting around the Barycenter once a month, round numbers, 27 1/3 days. So the moon is going really slowly compared to the spin of the Earth. And so if the north pole of the Earth is there, let me now put in, and I apologize that the high tides are washed out on this slide. I've got to do something about that. The rapid spinning, called rotation of the Earth, okay, drags that water of the tides that we've just created here, so that the high tide really isn't directly under the moon and away on the other side. The high tide is actually about 10 degrees ahead of the moon as the Earth rotates, as the world turns, and as the moon orbits. So the moon is orbiting once a month, the Earth is spinning once a day. And this rapid spinning compared to the moon's orbit is dragging the water so that the high tides are literally in this situation like that, rather than that. And that's a big deal. And the reason it's a big deal is that this water that is out here, I'll do it this way. The water that is out here, the moon over there, okay? This water has gravity. It has mass. It's pulling on the moon. And this water here, pulling on the moon there, is analogous to if I had a ball on a string and I spun around. Well, you know what's going to happen. The ball is going to spiral out. I give the ball energy by spinning around. The high tide water here, 10 degrees ahead of the moon, its gravity is pulling on the moon, giving the moon energy. Like I gave the ball energy on the string. All right? Leads to 2 other common beliefs. I just said, correctly, I hope, I just said that the high tide water pulling on the moon, the gravity of this water pulling on the moon, is giving the moon energy. And in the show that I did, all right, they rewrote it to say the water is pulling on the moon, giving the moon energy, which is speeding up and spiraling away, and will someday leave the Earth's orbit forever. And everything I just said is wrong. It is absolutely true. It is absolutely true that the moon is getting energy from the Earth, okay? But that energy is not the energy of speed. It is the energy, and I better not use the bottle. I'll let you visualize what would happen. As I lift this bottle up, okay? If I were to drop it, the higher I lift it, the faster it's going to go and the bigger mess it's going to make on the floor here, okay? The energy related to how far an object is away from, in our case, the Earth, is called potential energy. And that's the kind of energy that the Earth is giving to the moon. The moon is gaining potential energy. It is spiraling away from the Earth, but slower and slower. Because the farther you get away from anything that you're orbiting around, the slower you go, it turns out. Okay? And the other part of what I just said is, I said it goes faster and faster, and someday it will leave the Earth's orbit forever, which is what they said in this show. And the other part of that being wrong is it's not going to leave the Earth forever. And the reason is, as the Earth spins with the tide 10 degrees ahead of the moon, that water, the high tide, is literally, by the force of gravity or by the outward force, is trying to get back into a straight line here. And therefore, this high tide over here, as it moves, is moving against the ocean bottom. And every once in a while, these nasty continents get in the way. And that takes energy from the water. The Earth, as a result of this, is slowing down. So it's a case of you don't get something for nothing. We give energy to the moon. We lose energy by slowing down. Okay? And to close this part of the story, in about 15 billion with a B years from now, the moon will have spiraled away so much that the Earth's rotation rate, here's the Earth now, the Earth's rotation, spinning rate, will be exactly the same as the moon's orbiting rate. And from then on, the high tides are going to be locked in a straight line with the Earth, between the centers of the Earth and moon. That water will no longer be ahead of the moon, pulling it forward. And this motion here, well, you actually can see that today, because if you ever look at the moon, no matter what phase it's in, we always see the same side of the moon. The moon is literally spinning on its axis. This is the side of the moon we see. The moon is spinning on its axis at exactly the same rate today as it orbits the Earth. So we always see the same side, no matter what phase, no matter where the moon is relative to the sun, period. Okay? Eventually, the Earth is going to also be rotating, spinning on its axis at the same rate as the moon is orbiting it farther away than it is today. I'm sorry?
Why exactly will...
Hang on one second, they'll bring the mic for you.
So, will the speed of the Earth's rotation change? And if it does, why exactly? Because if the moon is getting more away from it, wouldn't that make the rotation of the moon take longer? That would mean the Earth will rotate slower. So
the reason the Earth will be rotating slower, and it is today too, by the way, I'll give you some numbers in 1 second. The reason the Earth is rotating slower and will continue to slow down its rotation rate is because of the friction between the high tide water pushing against the Earth. The high tide water is pushing against the Earth in the opposite direction to which the Earth is spinning. And it's a competition between the Earth's rotation and the friction created by the water pushing against the ocean bottoms and continents that is slowing the Earth down.
Is the number that big to slow the,
Let me give you...
Also,
Yes.
where did all the water of Earth come from if Earth was pretty much a predominantly rocky thing? Where did all the water came, and why doesn't the moon have water on it?
Okay, let me see if I can get all of those questions.
Okay.
The water came primarily from impacts of objects we call comets. Comets are literally icy bodies, and they, pulled by the force of gravity over the billions of years, especially early in the life of the solar system, about 4.5 billion years ago, there were lots of comets, frozen icebergs in space, and many of them were pulled down to the Earth. And also some of the debris that became the Earth in the first place was rocky debris with water molecules bound to them. So there was a combination of the material that formed the Earth in the first place. Yes, it was really hot, and some or a lot of that water was evaporated away, but some of it was still here, plus the impacts from icy debris, and comets are still here too, leftover comets. Back in 4 billion years ago, that's what gave us the water that we have. Okay? And the other question you asked was, I'm sorry?
Why isn't there water on the moon?
Oh, why isn't there water on the moon? First of all, there is. And second of all, there isn't that much, because the process of creating it, that impact, was so powerful when it splashed the debris into orbit. A lot of what may then have been water on the Earth was vaporized, given so much energy that water sailed away, because the molecules of water much smaller than the molecules of dust and rock. So most of the water is gone, but not all of it. And in fact, it's only recently that they've started finding water on the moon. Did I answer all of your questions? Okay.
So you assume that one day that the Earth's rotation will be the same as the Moon's rotation, but you know that if your assumption is true, that it takes 4.5 billion years for Earth's rotation up to 24 hours. But do you think that one day it will go into like 30 days for the Earth's rotation? It takes a long time. So I assume that it is true or not.
Another wonderful question. Let me give you some numbers. Okay? Calculations have been done to answer your question, probably because they knew that you were going to ask it. And the answer is, it will take, in round numbers now, about 15 billion more years, with a B, billion more years, before the Earth's rotation and the Moon's revolution around the Barycenter are the same rate, so it all stops spiraling away. Okay? 15 billion with a B. The sun is going to, in a gentle way, but we're not going to be here anymore, explode in about 5 billion years, so it really doesn't matter. Have I answered your question?
Okay. So we don't need to worry.
No, not so much. Not so much. Okay, so now we have the moon, the tide. Oh, and I'm sorry. Let me add, and I said it once before, but let me reiterate. The moon causes 2/3 of our tides. The sun, the other third. Okay? Same kind of interaction, same outward force, blah, blah, blah. And so I'm going to focus on the moon, but conceptually the sun is there too. And I'm aware of that. But okay, so I've given you all of this information. The question is, why should you believe me? And that is entirely relevant to any scientific presentation of any kind is, what's the evidence? This was first proposed, if memory serves, by George Darwin, that's Charles Darwin's son, in around 1905. I could be wrong by a few years there. This scenario I just described. And because it was known at the time of the Apollo spacecraft one of the experiments that they put on the moon. Let me show you. I actually had to contact NASA, and the guy who knew about all of these things is now living in Australia. And I had to email him to get the names of what each of these things is, because they're still there. Yes, we have been to the moon. Okay, the one I want to focus on is this device right here. I've labeled it corner reflectors. And conceptually, it is absolutely identical to the orange and red reflectors on your cars. You look at if you're driving a car, for example, another car is coming across the road, and maybe you can't see its headlights because it's going this way and you're going that way. You will still see it because on the sides of the car and on the front and back are orange or red reflectors that when light hits them, the light bounces off three sides in each reflector, you can take a look and see, and comes back in the direction from which it came. All right? And they're called corner reflectors because they're very similar to the corner of a room at the wall meeting three sides. And so the corner reflectors on your car, which help to keep us safe, all right? Those are the same as these corner reflectors put onto the moon. Probably cost $1 million to build this thing, 25-cent reflectors these days. And it just sits there. And then what happens, and people can do it, and it could be done here. Actually, I'm thinking of having students do it at the University of Maine. If you send laser beams to the moon, okay? We know the speed of light in great precision, even through the air. We know the speed of light, and we can therefore time the time it takes a laser beam to go from Earth to the moon, hit the corner reflectors, and it will then come back in the direction from which it came, and we can time the round trip. And this has been done since 1969. And what they found is that the moon is moving away from the Earth about 1.5 inches a year, about 4 centimeters a year. Okay? Just exactly what the calculations predict. But I said also the Earth has to lose its energy by slowing down. The Earth is and has been measured to be slowing down today about 1,000th of a second per century. So atomic clocks have to be readjusted regularly. And so the science of what I've just said and the experimental results are here. All right? So the moon has had a huge effect. But that then raises an interesting question. If the moon is moving away, therefore it must have been closer before. And not just closer, I'm talking about industrial strength closer. And how much is industrial strength? We don't know for sure. But in round numbers, the moon was once about 10 times closer than it is today. Okay? And at the same, yes?
So can I assume that the Barycenter is changing as well, right?
The question is the Barycenter changing? Yes.
Yes. So my question is, towards which continent is the Barycenter? It's lopsided somewhere, right? It's not at the center of the Earth.
No, good question. The question is, to which direction is the Barycenter centered? And the answer is, it varies continuously as the Earth turns. So as the Earth is turning, the Barycenter is always in a straight line between the center of the Earth and the center of the moon. So therefore, continually, the Barycenter is continually changing. Is that okay? Okay. All right. So it had to be closer. Best guess, around 10 times closer. We don't know the exact number, but about 10 times closer. And if the Earth is slowing down now, it has to have been slowing down before. So how fast was the Earth spinning when it first formed, or when the moon first formed? We don't know that either, but in round numbers, about 6-hour day. And it has been slowing down ever since. Let me give you an idea, because this is going to take us to the next concept that's entirely relevant about the presence of the moon. If the moon was 10 times closer for those of you who know these things, it goes as 1 over the cubed of the distance, 1 over the distance cubed. When the moon was 10 times closer, the tides were 1,000 times higher. Okay? And in Maine, where I live, the tides are typically about 15 feet now. So the tides, if Maine had existed back then, would have been 15,000 feet. 15,000 feet, and this is what was really happening, 15,000 feet, and the Earth was spinning 4 times faster. So instead of having every roughly 12 and a half hours tide cycle, high tide to high tide, okay, it had 1/4 of that, so every 3 hours. 15,000 feet of water was going inland, 15,000 feet of water was coming out, back and forth for hundreds of millions of years and longer as the moon spiraled away and the Earth slowed down. But if you think about that, that motion of the water over the young continental surfaces was scraping a huge amount of mineral content into the oceans. This is real life now. And that huge amount of mineral content then was what enabled life to start forming on the young Earth. The oceans were incredibly mineral rich, and therefore if, say, some organic molecules started forming and started making other organic molecules, there was plenty of material for the organic molecules to start growing and whatever the process of forming life in the first place, which we don't know.
Are the timescales for these processes consistent with what we know in biology? What I'm meaning is, by the time this was happening, the minerals being poured onto the oceans, was that around the time when we believe life originated?
I honestly do not know what the earliest life that has been discovered on the Earth is. Does anybody know that number these days? 4 billion years ago. So about 600 million years after the Earth formed, then life started forming as far as we know today. By 600 million years, with that scouring of the ocean surfaces for that period of the scouring of the continental surfaces by the oceans, there would have been plenty of mineral content in the oceans to allow life to start forming. Does that answer your question? Okay, so the formation of life occurred very early on in the life of the Earth, because the minerals in the ocean were so rich that if life started forming in one place, let's imagine that what I just told you hadn't occurred, then the only way that the minerals that formed life in the oceans would have gotten there in the first place would have been, number 1, from river runoff, and number 2, from debris coming out where the continents are moving apart. And those regions, compared to the total volume of the Earth, are tiny. So if life had started forming, let's say, near a river outlet, because there were some minerals there in a world which never had those huge high tides, and now we're getting on to what if the moon didn't exist, then the slightest disturbance, a windstorm, and I'll get to that in a second, could have pushed the mineral content from the river runoff, spread it out so much that there wouldn't have been enough minerals for the next generation of life to form. In a mineral-rich ocean as we had, there was plenty of minerals everywhere for life to begin forming. Okay? Any further questions on what I've been saying?
I didn't quite understand why the back and forth movement that the tide do. Why does that occur?
That's a very good question. Yeah, and I'm sorry I did not make it clear. The high tides, we're talking about 3-mile high tides going inland for 3 hours and then coming back out for an hour and a half and then coming back out again. That water is rubbing against the ocean bottoms. Remember I was talking about how the friction between the tides and the Earth is slowing the Earth rotation down today? The rubbing of the water on the continental surfaces, literally, there was friction. And that friction rubbed off the top layers of the continents and brought that material as minerals dissolved in the water back into the oceans. Is that conceptually? Go ahead.
Why is there back and forth movement in the first place?
I'm sorry if that wasn't clear. If this is a high tide here, okay, as the Earth is turning, here's the moon. As the Earth is turning, okay, the water is rubbing against the surface of the continents. And if the Earth is spinning really fast, as the Earth turns, the water is trying to be pulled back, is creating very high not waves, but like essentially like you would imagine a tsunami, huge waves of water being pulled by the moon, huge waves of water being pulled by the moon when it's much closer to it than it is today, trying to get back in a straight line. So this water is being pulled and the Earth turns, and this water flowing as it is today, but much, much, much higher and much faster, scrape the Earth's surface much more than it does today. Is that? Okay. So now I believe we have the building blocks of what if the moon didn't exist. So let's take a look. All right. And here are the pieces that we'll take away as we go through the end of this talk. First of all, it made the primordial soup that I just described, the tidal force from the moon on these enormous tides. So, well, it's not as high as that, but it's the biggest, highest picture I could find. So, all right. It caused the Earth to have seasons. You may recall I showed you that the Earth's axis was tilted over by the impact. And very briefly, let me just tell you that tilt causes the seasons. And it causes the seasons because the Earth's axis of rotation doesn't change direction. The axis here is the same direction as here, all the way around the sun. And therefore, at different times of the year, the sun is at different places in our sky because of this tilt. So, for example, in winter, the sun rises to its highest point very low in the sky for you here and for me in Maine. Compared to in the springtime, it rises higher because the tilt of the Earth's axis is pointing more towards the sun as the Earth is going around from here, that's our winter time, to here, our springtime. And in the summer, the sun is tilted more towards the northern regions of the Earth, which is why in summertime, the sun is higher in our sky. So that, and therefore, I should say, that the energy from the sun is more concentrated here, the circle is smaller, than it is here. The same energy is more spread out during the winter. And therefore, we have the seasons. And yes, please.
Does a planet require an impact to have an axis that is off-kilt?
An excellent question. The question was, does a planet require an impact to have a tilted axis? If you had asked me that question 6 months ago, I would have said no. And the reason is that in 1993, computer simulation showed that without a moon, the axis of a planet is very unstable. It can change from no tilt, no seasons, to serious tilt, serious seasons. But about 6 months ago, other computer simulations showed that even without a moon, the axis tilt may be stable. And if the moon had, or the planet had not been hit, it would probably still be like this and would be probably stable. So in that case, the answer would be yes. Okay. It's work in progress. That. Okay, onward. So let's see. It may have, I changed this from the original, that it's stabilized to it possibly stabilize the Earth's axis of rotation. So that, which is what the gentleman just asked, and that's a definite maybe. Work in progress, as I said. It has slowed the Earth's rotation. Without it, well, you know the answer. It moderated the weather. The faster a planet spins, the stronger the winds are. So with a 6-hour day, there would be seriously different, profoundly different winds and weather than there is today. The rotation rate of the Earth determines the biological clocks that we all have. We and other animals have internal biological clocks which synchronize to the day. And the cycle of everything that we do is based on our biological clock synchronized. I mean, that's why sometimes if you stay up too late and you get up too late in the next morning, you're groggy and you don't feel as, because you're not in sync with your biological clock. And so the biological clocks we have are synchronized to the Earth as we know it. Imagine what it would be like to have to do what we do every day for a 6-hour day. Not going to work so well. It also provides light. It serves for navigation, and I just learned an interesting thing from the gentleman from Malta who told me that the sea urchins respond to moonlight. Their motion and therefore their ability to be farmed varies with the phases of the moon. And that's certainly not the only example, but it's a really interesting one I'd never heard before. So the amount of moonlight and the location of the moon at various times has an impact on a variety of biological life. It has been a wonderful goal from a sociological point of view for humans to go to. It was a target we could reach in the 1960s before they had invented computers. Or, well, they had computers, but nothing compared to what we have today. Your cell phone has more computer power than there was on Earth in the 1960s. So we could never have gone to Mars then. We still have, it's going to be a challenge to get there today. The moon, perfect, just what we needed. Okay? And perhaps the most important thing, romance. All right. And finally, if the moon had never existed, with all I've told you, hopefully none of this will be news, but I'll put it up there anyways. The day would be between 6 and 8 hours long. It would have slowed down slightly due to the tides from the sun, but the sun's tides would have been the same from the day the Earth formed, or the oceans formed, till today, because the sun and Earth have always been the same distance away from each other. So tiny, tiny change in the rotation rate due to the tides created by the sun. And that would have been true like forever in the existence of the Earth. Vastly different weather patterns. I mentioned the rapid rotation and the complete change in the wind structure and the weather on Earth. Completely different, much more challenging than life has had as far as the weather is concerned on Earth. Vastly different seasons. In the sense of if there was no tilt, and it never was, there would be no seasons. The primordial soup, the flowing, as I said, from the oceans and from the divides that separate the continents, was a much, much, much slower process than the tidal formation of the primordial soup. And the so what about that is that it is entirely likely that life would have started forming much, much later, billions of years probably, later than it did on Earth, if at all. Okay? And the life forms. Imagine what life would have to have been to survive on that world. Please.
Does this mean that if we're going to look for life in other orbiting bodies, that we should look for planets that have a moon or something like that?
Everyone hear the question? It certainly would not hurt to look for a world, a planet that is a place where water can be liquid, that's criteria number one, that does have a moon. But if that world has been around it, orbiting around its star for billions and billions of years, then by now it may well have life, even if it never had a moon. So the short answer is yes, the long answer is no. Yes, please.
Yeah, a point of clarification. Are you referring to the moon as the body that hit Earth?
No.
Or the accumulation of debris after the hit?
The accumulation of debris after the Earth. I think the body that hit the Earth is called Theia. Is that? I'm sorry.
So yeah, if it's called Theia is the reason why we don't have a 6-8 hour day. It's not the moon. And second thing, if Theia hit the Earth and the debris accumulated as the moon and left completely, the axis would have been tilted just the same. So it's not, if the moon didn't exist, I think we should be in the same position exactly, except the sunlight and werewolves, probably.
It is no, what he says is an extremely good point. If a body had hit the Earth and had not splashed off material that could form the moon, it may well have tilted the Earth. It may well have. However, I haven't seen the computer simulations, but the amount of energy it would take of the impact to tilt the Earth's axis this much may also have required or led to the splashing off of debris to form a moon. In other words, it's possible that you could get one without the other, but, and again, this would depend on what the computer simulations show. It may be that if you were able to tilt the Earth this much, you would also have to splash debris into orbit. And I don't know the answer because I don't know that the work has been done.
Right, second question. As the moon moves away from Earth, the Barycenter will actually leave the body of the Earth.
Yes.
So will that affect the tides eventually?
Conceptually, no. The behavior of the Earth around the Barycenter doesn't matter if it's inside the Earth or outside the Earth. It will still go around the Barycenter conceptually in the same way as it does today.
Tangent on that, could a near miss of a massive object tilt the axis?
The short answer is no, because the time of interaction would be too short, and the effects, which would be tidal, by the way, would also probably be too small to make such a profound change, especially because the Earth was rotating so rapidly. It's harder to tilt a rapidly rotating object than a slowly rotating one. Yes, please.
So, let's see. How likely is it that the Earth would have been rotating so quickly if there were not the moon-forming impact? Because, I mean, if you look at the other inner planets, they're all rotating. You know, Mars rotates at about 24 hours, and it has tiny moons. And Mercury and Venus have, 100-some day rotation periods, and they don't have moons at all. So, maybe if not for Theia, we would have a slow rotation like Mars or something.
Conceptually, it is entirely possible that we would, in the sense of the debris that formed the Earth in the first place may not have had as much net energy of rotation, called angular momentum, as our Earth did. However, we don't know that yet. In other words, computer simulations, to the best of my knowledge, haven't shown it. We do need to wrap up. One more quick question?
I was just wondering if the effects of a ring formation like Saturn has instead of a moon would be the same as if there was no moon.
It turns out that the gravitational mass, the mass of the rings of Saturn is so small that they can't form a moon. It is possible that the Earth could have had much less stuff splashed off and not formed a moon. In that case, the simulations show that ring would fly away. Okay? And with that, I will end my talk. Thank you very much.